In 3 dimensions, we can follow similar arguments. Periodic boundary conditions in 3 dimensions are, however, absurd if we treat them too literally. We would then need to imagine a crystal where each face is joined to the opposite one in a long loop, and that's something we can't do sort of simultaneously in 3 dimensions. So we do have to recognize that what we're doing is constructing a model we hope will, in the end, give us a useful way of handling this quantum mechanics of crystals in practice. We do this even if, taken too literally, this model does not quite make sense. This is another example of a consequence, mathematically, of idealizing a system, specifically here by introducing the infinity that the crystal fills all space. That infinity does not, of course, correspond to physical reality, and, not surprisingly, we have to use another mathematical trick to get us out of the consequences of that. However, this approach is, in the end, justified as a model because it does give us useful results that do agree with experiments. We do, however, sometimes have to be careful, especially when handling nanostructures that are quite certainly not infinite and quite certainly have quite hard wall boundary conditions at their surfaces. Even there, though, it turns out that the ideas we get from this idealized view are still quite useful. So, periodic boundary conditions in 3 dimensions, though they have some absurdities if we take them too literally, do give us a useful model. In particular, we have a model that does allow the same simple definition of periodicity as in an ideal crystal, while still allowing us a way to count the available states in a reasonably sensible way. So, to construct the Bloch theorem in 3 dimensions, we simply propose a straightforward extension from what we did in 1 dimension. And now we're going to have, for one statement of our Bloch theorem here, that as we move over by any crystal lattice vector, here written as little a, the wave function will just be the original one, but multiplied by e to the I k, now a vector, dot a. Or equivalently, in our other way of writing the Bloch theorem, we would say that the wave function at position r can be written as a function that's the same in every unit cell, now a function of a vector position r, times e to the I k dot r. And again, these u of r's are the same in every unit cell. So u of r plus any crystal lattice vector here would be the same as u of r. So, with 3 crystal basis vector directions, 1, 2, and 3, which we could think of as x, y, and z, but they don't actually have to be orthogonal in general, and with lattice constants, that is, repeat distances a1, a2, and a3 in the 3 different directions, and numbers of atoms n1, n2, and n3 in the 3 different directions, then we would have values of k1 that would have to be corresponding to n1s taken from this list, so 2 pi n1 over capital N1 times a1. And similarly for the 2 other components, for k2 and k3, which would be the components of the vector k in the directions 1, 2, and 3, respectively. Note, incidentally, that the number of possible values of vector k is the same as the number of unit cells in the crystal. Of course, we have to formally drop the one extra value here at one end or the other of this list. But that's an important thing to remember. The total number of distinct k values, vector k values, is the same as the number of unit cells in the crystal. Now we come to an idea called the reciprocal lattice. This is actually quite straightforward, although it can get confusing on the way through here. We see that we have allowed values of k1 and k2 and k3 that are each equally spaced, now with separations 2 pi over L1 for the separation between allowed k values for the k1 direction, and 2 pi over L2 in the k2 direction for the separation between adjacent allowed k2 values, and similarly
2 pi over L3 for the separation between allowed K3 values. And these are respectively, of course, along the three axes, which, as I said, might be x, y, and z, or they might not. And the lengths of the crystal here, of course, in the three different directions, as is implied by the bottom lines on these equations here, are given by these simple expressions. The length in direction 1 is capital N1 times A1, and so on for the other two directions. Now, we could draw a three-dimensional diagram now with axes K1, K2, and K3, and mark in that three-dimensional diagram all of these allowed values of the vector k by marking dots at the corresponding coordinate positions given by what's our k1 value, our k2 value, and our k3 value. So, plotting in 2 dimensions, just because that's easier to draw here, what we're imagining now is that we have these dots along one direction here, maybe this is k1, that are equally spaced, and similarly along direction k2, we have another set of equally spaced dots. And the separation between the dots in the k1 direction will be the delta k1 we just wrote down, and similarly in the k2 direction, it will be the delta k2, as we similarly wrote down. And this set of dots, as you can see, also mathematically constitutes a lattice of points. And this kind of lattice is what is called a reciprocal lattice. Now we can imagine, if we like, that each point in this reciprocal lattice has a sort of a volume surrounding it. So I've sketched that here. This is the volume, again, of what looks like a brick of some kind in our lattice. And we could see that if we took these bricks here, we could stack them side by side to fill up the entire mathematical space that we're drawing here. And also, we presume, in the third dimension. And these bricks, these volumes, would touch one another, and they would fill all of the mathematical space that we're talking about here. For our cubic lattices that we're going to be thinking of, we can define these separations here as we've been writing down. So delta K1 is 2 pi over L1, delta K2 is 2 pi over L2, and similarly for the third dimension. Again, for cuboidal lattices, these volumes in K space, the size of these bricks in the mathematical space we're now working in, will be this kind of a volume here. Note I've got a subscript K. It's the volume of this brick in this mathematical space, and it's just the product of the lengths of the brick in each of the three directions. So this is our delta VK, we're calling it. And explicitly, given these formulas here for delta K1 and delta K2, and similarly for delta K3, this is a formula then for the volume of this brick in this mathematical space we're working in. Now, the crystal itself has a total volume that is the product of these three lengths. These are the lengths of the crystal in the three directions. And for a cuboidal system, we are going to get a volume that is just the product of these three lengths. Then we can talk about the volume of this brick here in K space. That's the mathematical space in which this diagram is drawn. Therefore, the volume of that brick is 2 pi all cubed over the product of these three lengths, which turns out to be 2 pi all cubed over the volume of the crystal. Now, this is where it gets confusing, at least at first. The dimensions of this volume, the volume of this brick, we see are 1 over real volume. So this is a K-space volume, as it's called, and the physical dimensions of K-space are 1 over the dimensions of real space. That's one reason why this is called a reciprocal space. But it's a well enough defined mathematical space. It's just that physically it has rather odd dimensions. It has dimensions for a brick in this space or a unit cell in this space that are dimensions of 1 over real volume. So with this specific K-space volume that we've just worked out, around each point in K-space, we could, if we wanted to, define what's called a density of states in K-space. How many of these bricks are there per unit volume in this mathematical space we're working in? Well, we know the volume of these bricks, the volume of each brick, is what's given here. And so the number of those bricks per unit volume in K-space is 1 over the volume of one brick. That would be true in ordinary real space if we had a brick of a given volume, and a total number of bricks per unit volume of ordinary real space would just be 1 over the volume of the brick. So we have a density of states in K-space that is 1 over the size, the volume of one brick. But here's our formula for the volume of one brick. So the density of states in K-space is the volume of the crystal divided by 2 pi all cubed. This density of states in K-space that we've just written down is proportional to the total real volume of the real crystal. Here's our volume of the real crystal here. So more commonly, we define a density of states in K-space per unit real space volume. And that is just the number 1 over 2 pi all cubed. We call this G of K the density of states in K-space per unit real volume of crystal. And it's just a number, 1 over 2 pi all cubed, for quantum mechanical calculations in crystals. It doesn't matter what the crystal actually is, as long as it's crystalline in 3 dimensions. The mathematical concept of the density of states in K-space per unit real space volume, at least as we proved it for these cuboidal volumes here, is 1 over 2 pi all cubed. And this turns out to be a very useful concept as we go forward. It's a slightly strange and at the moment rather abstract mathematical concept, but it turns out to be physically very useful, and we will get used to it as we work with it.